Swayam Prabha. Digital India. Educated India.
We'll take an example of that as well. So let's see, we'll take a classifier with the 6 rules. Here is the classifier with the 6 rules, and there are 3 dimensions here, F1, F2, F3. So F1, F2, F3 is just the name. You can call it as D1, D2, D3 as well. There is no issue with that. And it has got the port range as well and the port as well. So let's try to construct the field level try for this set of the rules or this classifier. So as usual, I start with the first dimension. So now every node at the first level root R1 to R6 is applicable. That is my root node. And at the level 1, what are the unique combinations I have got? These mean 1, 1 star, 0, 1 star, 1 star, and then the star itself, and then the 0 star, 0 star. And that's how they look like. When the 0, 1 star is the prefix, rule R3 is applicable, this case, and R5 is applicable because 0, 1 star is a subset of the 0 star. So still R5 is a potential candidate. And both of these are the subsets of the R6. So rule R6 is still the candidate. On the input 0 star, only R5 and R6 are the candidates because R6 is actually a superset of the R5. And on the star, anyway, only the rule R6 is applicable. On 1 star, rule R1, R4 and R6 are the potential candidates. Yeah. And on 1, 1, you got R1, R2 and then R4 and R6 as well. So R4 is a superset of both R1 and R2. 1 star and the R1 and R2 are 1, 1 star, 1, 1 stars. So that's the first level nodes actually look like. Now again, I take one node at a time and then apply the possible second level prefixes and then see how the branching look like. So here is the second level branching from the node R3 to R5 to R6. For the rule R3, 1, 1 star is one unique prefix. And then for the rule R5, 1 star is another prefix. And for the rule R6, 0, 1 star is another prefix. So that's why I got 3 branches originating from this particular node in the trie structure. So I continue doing that from the node R5 and R6 as well. Again, there are 2 branches. For the R6, there is only 1 branch. And again, from the R4 and R6, there are 2 different branches, one to the R6 and one to the R4. And there are 3 different branches from the, in fact, 4 different branches from this particular node, the second level set of the nodes. So this is how you construct the type. Now all the unique combinations for the level 2 are also taken care. Now let's add the third level dimension into the same trie structure and then see how the look like. So from the second level division R3 to R5, what it says is when the rule R3 is applicable, the port number need to be 3. So only then the rule R3 is applicable. So with the label 3, I added the node with the node level 3 and the edge level node level R3 and the edge level 3. And for the remaining cases, so what is the rule? R5 says it is 1 to 5, but the 3 is more specific than the 1 to 5 range. And R3's prefixes, these two are also supersets of the R5 as well. So 3 is more specific. So rule R3 is more specific. I separated it out. For the remaining set of the cases, what are those? Between when the port number is 1 and 2 and when the port number is 4 and 5, I need to use this rule R5 to classify that particular packet. So that is why I wrote this 1 to 2 union 4 to 5 as one branch for this particular node. And I continue doing this. So for the rule R5, again 1 to 5 is there. So that is fine. For the rule R6, only 10 is required, so that is fine. For rule R4 only 15 is required, that is fine. And for the rule R1 and R2, there is an overlap. So R1 is a subset of the rule R2. When the 6 is there, so I'm going to take the I'm going to classify that particular packet with the rule R1. That's what the label. And when the range is in between 4 to 5, excluding the 6, and then 7 to 8, I'm going to apply the rule R2. And similarly, from this branch, entire 4 to 8 range, when the prefix at the first level is 11 star and 00 star, and then in between port number can be any between 4 to 8, then I apply this particular rule R2 and then do the classification. So that's how you segregate. If there is an overlap, then you look at the more specific rule sets and give them the preference, take out that branch separately, and the whatever is the remaining portion is there, that is actually used for the other possible rule set that are there in the structures. So that is how we actually construct the field level trie. This is basically you start with all possibilities, then slowly segregate what are the rules that are potential candidates applicable for this particular prefix combination and the port number combination in the sets. Okay, so with that we'll end the discussion on the trie structure, and we move on to the another kind of the interpretation for the same packet classifier. So this interpretation or the analysis is based on the geometric notation of the classifier. What we did is, assuming all the dimensions are having the prefix values as the prefix values in each of the dimension. So you can think of this as multi-dimensional hypercube, and then if a packet comes and the classification action is basically finding out which of the hypercube in the entire structure, multi-dimensional structure, this point is actually particularly falling in. So that is what there are nice geometric algorithms which can actually find out in which of the hypercube the particular point is actually falling into. So although we don't look into those geometric algorithms such, but what is the notion behind how do we interpret this classifier rules into that geometric interpretation, that we will take a look into in this particular discussion. So let's say again we'll take a simple example on the two dimension D1 and D2, and the classifier has got rule R1 has got 00 star and then a 1 star, and rule R2 has got 10 star and then a 1 star, and rule R3, let's say this is star and then 1 star. So what I do is, there are two dimensions, and now I need to look into this is a point falling in the two-dimensional space. So let me draw one dimension for a particular this, let me call it as a D1, and then this dimension D2 is on the y-axis. So I'm going to divide this x and y-axis into several ranges. And looking at the prefixes, I'm going to mark this particular area is actually falling into this particular prefix. That's what the geometric interpretation is. So here I'll start with on the x-axis a value with 0, 0, 0, 0, and then divide this into 4 phases from this area to this area. The values with the prefix 0, 0. And these two bits are varying. So I have 0, 0, 0, 1, 0, 0, 1, 0 in between, and 0, 0, 1, 1. So the moment I cross this area, I got 0, 1 and then 0, 0. This will continue up to 0, 1 and 1, 1. When I cross this area, this is 1, 0, 0, 0. This is 1, 0, 1, 1. 1 1 0 0 1 1 1 1 or 1. This is the division for the first dimension. Is the prefixes actually fall into one of these regions. So for example 0 0, where exactly the region 0 0 is falling. So particularly in this range, these four values are having the prefix 0 0 star. So these four values. Similarly on the y-axis as well, I am going to create such similar division. This is 0 0 up to 1 1 0 1 0 0 and 0 1 1 1, and this is 1 0 1 0 0 0, this is 1 0 1 1, and 1 1 0 0 1 1 1 1. And I can draw a line from here to here, here to here, here to here, and here to here, and also the vertically from here to here, here to here. So this is a two-dimensional grid, and what it is saying is, looking at the prefixes on the dimension D1 and D2, we need to identify what is the particular region on which this particular point is actually falling. So for example, let's take the case of the R1 is 0 0 star, and then the dimension D2 is 1 1 star. So where exactly on the dimension D1 0 0 star is appearing? So it is these four values are this particular range from 0 0 0 to 0 0 1 1. So this range is actually indicating 0 0 star, and the second dimension on the y-axis it is saying 1 1 star. So where exactly 1 1 star is? These four values are indicating 1 1 star. So I am going to mark this region as the region for the rule R1. So if the point falls in this particular box or the two-dimensional space, then I am going to classify that with the rule R1. So this is the place where the R1's rule is applicable for that particular packet. Similarly, for the rule R2 says the dimension D1 says 1 0 star. Where exactly is 1 0 star? This is the region where 1 0 star is there in the x-axis on the dimension D1, and the second dimension is still 1 1 star. 1 1 star is in the same region. So this is your rule R2. This entire range is R2. And if you come to the rule R3, the dimension D1 says this is star. So what is star? Everything from here to here is star, but the dimension D2 says still it is 1 1 star. 1 1 star is the entire this region is actually 1 1 star, but two of them R1 and R2 have already occupied two spaces. They are more specific than the rule R3. The remaining part, two boxes, I am going to classify R3 with the R3. So if at any point of time, the more specific rules are labeled. So if there is an overlap here, in this case, R3's range is from here to here, but R2 happens to be a subset of that entire range. Whenever the point falls in this particular range, I am going to do the classification with the rule R2. Whenever the point falls in this range, I am going to do the classification with the rule R1. But when the point falls in this and this box, then I am going to use the rule R5. That is what the geometrical interpretation is. So you can extend this to 3 dimension, 4 dimension. So although drawing on this page with the 4 dimension is not possible to indicate, but you can imagine, just like the machine learning people visualize this as the hyper dimension. So 2 dimension, 3 dimensions, n dimensions, you can go, and then in which of the hyperplane the point is actually falling based on the values in the packet, then you decide which rule to apply. Once I label the hypercubes with the appropriate name, then rule set, then I can actually use that rule to do the classification. So let's take one more example. Here is the a classifier with the 5 rules from R1 to R5, and these are the prefix values for the dimension D1 and D2. And when I do the classification, so on the 2-dimensional grid, this is what the labeling look like. So rule R1 is 0 0 star. So this is the 0 0 star region, and the dimension D2 is also 0, 0 star. This is the reason where it is 0, 0 star. So that's why I labeled it as R1. And R2 says 1, 0 star. 1, 0 star is here. And but the dimension D2 is just the 0 star. So in all the four these two boxes, and particularly because this is changing, only one bit is constant across these four values, which is 0. So I take this as the reason. So I label this and this box as the label R2. Similarly, R3 is having 1, 0 star. So the same 1, 0 star. And the second level is 1, 0 star. So 1, 0 star and the y-axis is this region. That's why I labeled this as R3. And when I go to the R4, this is 1, 1 star. 1, 1 star is in this region on the dimension D1. And similarly on the dimension D2 also it is 1, 1 star. 1, 1 star in the dimension D2 is this one. That's why this is labeled as R4. And when I come to R5, this is star. Star indicate the entire this range on the x-axis, but the y-axis is 0, 0 star. So 0, 0 star is these four values themselves, but R1 and R2 have already occupied the space. They are more specific than the R5. So now the remaining two boxes actually I label with the R5. So that's the labeling. So it is not necessary that here in this case some of the boxes are not labeled with any of the rule. So if a packet comes with those attributes, I will not be able to do the classification. So this classification is not complete, meaning for all combinations of the values that you can find, you don't have the labeling done. So normally, in order to make this complete, what we do is add a rule which is more generic, something like this, that we call it as the R6, and star, anything doesn't matter, whatever is there. So you just label. Once I do the labeling for the rule number R1 to R5, they are already there. Remaining all boxes are now labeled with the rule R6. So that's how the classifier made complete. So if you have such a rule, if every box is labeled, then the classifier is said to be complete. So I can write R6 in the this is 6. And remaining all boxes. Now this classifier is complete. So maybe we'll take one more example. Here is a classifier with the 7 rules. I think we used this example earlier as well. And if you take this classifier 7 rules, how on the 2-dimensional space the labeling would look like. Again, rule R1 is 0, 0 star, and on the dimension D1, that is this space, and the dimension D2 is 1, 1, 0 star. So you can see this 1, 1, 0 star. 1, 1, 0 is only for these two cases values the 1, 1, 0 star is applicable. So that's why I labeled this with only and but for the remaining cases R2 is applicable. It is still R2 is on the dimension D1 0, 0 star, which is still this space, but it is 1, 1 star. 1, 1 star is applicable in the entire range, but 1, 1, 0 star is a subset of 1, 1 star. So that's why this is more specific than I have labeled it with R1, and the remaining space of the same box is labeled with the R2. And similarly, for the R3, it is 1, 0 star. 1, 0 star is here. And on the y-axis, this is 1 star. 1 star is applicable from here to here. That's why these two boxes are labeled with the R3. And for R4, this is 0 star. 0 star is applicable for these two cases. And then 1, 0 star, R5, R4, this is 0, 1 star. So 0, 1 star is applicable in this range. These two are labeled with the 0, 1 star, R4. And for R5, it is 1, 0 star and with the 0 star. So these two are labeled with the R5. And for R7, this is the star, entire range. And then the y-axis is 0, 0 star. So entire these four boxes are labeled with the classifier rule R7. So that's how you build the geometric interpretation for the classifier. So that is one kind of the interpretation that you can bring. And if you have an algorithm which can point out in which of the hyperq space the box, the point is actually falling. Point means the attributes, whatever you are picking from the packet and where it is actually falling. You actually use that particular rule, whatever action that particular rule says, you apply that rule to that particular packet. So you can use this interpretation to do the classification. And we also saw some of the heuristic mechanisms earlier as well. But those are not the only heuristics that you can use. There are other heuristic based algorithms that you can use to do the packet classification mechanisms. So here is one. Let's take the simple example. Here is the classifier with the 6 rules, and there are 2 dimensions. So dimension D1 is the destination IP and dimension D2 is the destination port number. And this is the action that you need to take on this particular rule set. So what optimization that this heuristic algorithm brings is, it is based on the observation that some of the field values for certain rules are common. So for example, rule R1 to R3 has the same set of the destination IP address, but with change of the port number values. And similarly, rule R4 to R6 has got the same set of the destination IP address, but the port numbers are changing. Can we exploit this kind of mechanism? This is not very uncommon. So if you have for different applications, you want to treat them differently. For the different port numbers, you want to assign different priority and actions as specified in this action list. When the port number on the same destination IP address, when it is 80, then you take this action. When it is the port number port 21, you drop. Port number 25, you drop. So that differentiation, the rules can actually specify such kind of a differentiation. Now, can I exploit this kind of the rule sets in my classifier and build some kind of the structure which actually allows me to do the lookup quite quickly, number of the comparisons quite quickly, and then do the classification or to decide which action to take. So, given the classifier is there and the rules are there, what I do is I'm going to extract the unique destination IP fields or the prefixes from that rule set. And then in this case, if I want to do the matching, when the IP address 10.10.10.10 is there, this is the 32-bit field, but it is repeating 3 times. Can I use this comparison to instead of doing if this rule fails, then I need to go and examine this one and so forth. So can I reduce the storage structure? This is not going to not only take the storage structure more storage. I need to store this structure 3 times because the IP address is appearing 3 times, and then the port numbers as well. So I can bring a slightly optimized version of this question, which is by instead of storing the IP address 3 times, I am going to store 1 time and then take an index to the second level table. And using the label in the second level table, I am going to do the classification. So let's take a look at how it look like. So I'm going to transform this every action that I'm having in this particular action field, I'm going to assign a number. So what is that number? Send to port number 3 is the action number 4. Drop is action number 5. So wherever drop is there, I'm going to write 5. And then send to port number 3 is action 4. And then send to port number 11 with the priority is action number 6. So the labeling is done. Once this is done, the next level step that I'm going to do is take the unique IP addresses in the first level field and then create a table for every unique destination IP address. An equivalent ID is assigned. So, for example, for 10.10.10.10, I'm going to assign the ID 0. for 20.20.20, I am going to assign an ID of 1. So now the table structure, earlier I had to compare this with the 6 number of the entries if I go linearly one by one. But now what I did is, by writing this, there are only 2 entries because many times the same entries are repeating. So I am going to assume whenever the equivalent ID 0 is going to be 10.10 interpreted as 10.10.10, and then I take the further action. So this is for one dimension, and for the second dimension destination port number also I built a similar structure. So destination port number, unique destination port numbers are these 3. Their IP address are 2, but the port numbers are 3. So every time I look at the nearest 2-digit n-digit binary number which is required to uniquely assign a number, an equivalent ID for this port number range. So for 80, I am going to maybe assign 00, for 25, I am going to assign 01, and for 21, I am going to assign 10. And now I will combine these 2 and build a table which is something like this. When the first level is 0 and the second dimension level is 0000, I take the action 4. When the first level, the equivalent ID 0 and the second level, this one is 01, I am going to take the action number 5. These are coming from the previous table that is there. So we just assign these 4, 5, 4, 6, 5 number, and using the same number I am now combining and labeling. So when the first level label is 1 and the second level is 00, you take the action 6 and so forth. I am going to build the action. So by doing this kind of the alteration into the table, what I am bringing is actually a table which is occupying more the number of the repetitions you have in any one of the dimension, the more larger the table structure look like. So instead of that, if I assign to ID, equivalent ID, I'm going to compress the table and occupy less space on the router, and you can store a larger classifier structure in the routing table. That is one heuristic that you can bring. And if you do a first level application, as long as the unique combinations are limited, there will be a substantial reduction both in the first level table and also in the second level table. So second level table, in the sense this combined table, since you are going to assign the binary numbers, unique numbers to those fields which are of 32 bits and 16 bits, and you combine them into using only maybe 2 or 3 bits or whatever the number of the bits required, then the second level table structure will also be substantially reduced, and it is more quicker to search in this second level table. Thereby you bring the speed of the operation. So that's another heuristic based mechanism you can use to do the packet classification quite quickly. And the last thing that I want to discuss is, again, if I want to do the lookup or the classification on the hardware, we understood that earlier TCAM based memory is the one which is used, and it can work very well with the when the dimensions or the values are in the form of the prefixes. But interestingly, what we noticed is the values inside some of the dimensions need not necessarily be in the form of the prefix, but they can take the ranges, particularly port numbers. So this leads to a very challenging problem called as the range expansion. So if I want to convert the ranges into prefix format, if I have let's say the port number is 10, it is 10, then I can convert it into a binary number. So the binary equivalent of this one is 1010. This itself, although there is no star here, but this I can treat it as the prefix format. As long as it is in the binary format, it's okay. But since the destination port is not a unique number 10, but it is in this range, what this what in order to convert this into a prefix format, what I need to do is to expand this range with the individual rules. So as many number of the what is the range that is specified 1 to 10, those many times the rules are replicated. That is where the enhancement of the actually takes place. This is called range expansion. So I am going to replace one rule and have an equivalent rule for every unique destination port number in my classifier, and you basically create 10 rules and then convert this destination port into binary format, into prefix format. This I can represent as 001, this I can write it as 0010 and so forth up to 1010. And instead of writing 1, 2, 3, 4, 10, I am going to write these values in this space. So that's the destination IP address is also in the prefix format, and also the destination port is also in this prefix format. Then I can use the TCAM memory to do the comparison quite fastly. Now the question is, this range expansion problem can be quite tedious to do when you do the expansion. So for example, if the destination port number is between 1 to 65,000 or something like this, then there are 65,000 rules created inside my classifier. One rule actually expanded to 65,000. That's actually quite a large number of the rules. So this is going to be challenging both for the storage perspective and also for the comparison perspective. So we need to handle this range expansion problem. And one way to do the handling that expansion is to compress, look for the opportunities to merge the rules inside the table, and then see as long as the action taken on that one is common, you can keep merging the rules which are adjacent, and then try to bring down the overall number of the rules. So let's say take the example, what kind of the prefixes can be merged. So here is one prefix which is 0010. And the second prefix is, let's say, 0011, and these two are differing by 1 bit. As long as the action taken for these two cases is common, what I can do is I can replace these two rules with a star and then take the action 5. I am going to basically look for such merging opportunities. As long as the action taken is common, I can keep merging them and get a prefix which is smaller. And also the overall number of the rules should be reduced by virtue of that. What I cannot merge is, if I have a rule which is in this format, although these two are differing by 1 bit, this I cannot replace it by another. So only the least significant bit in this area, which is, this is not possible. This is okay, but this is not okay. So like this, I am going to merge the adjacent rules inside my classifier and then get a reduction on the number of the rules. So let's go back to the same example. If my port number range is in between 1 to 10, how many number of the unique prefixes that I'm going to get? So as I said, there are 10 rules that are created for this one. So let me convert those into the binary: 001, 0010, 0011, 0100, 0101, 0110, 0111, 10000, 10, okay. So this is the set of binary values that I get. Now I can see what are the rules that, what are the adjacent values that I can merge. So for example, these two can be merged. They are differing by 1 bit. I get a smaller prefix 001 star, and these two can be merged to get a prefix 010 star, and these two can be merged to get 011 star, and these two can be merged to get 100 star, and this is 1010, and this is 0001. So from the 10 prefixes which is there in the previous case, now we landed up into to 6 prefixes. Now, are there any further compressions possible? So there is one more possibility. These two can be merged to get 0, 1 star, because these two bits are pairing. As long as the accent is common, I can get this prefix as a 0, 1 star, and this is 0001, 001 star, and this is 100 star and 1010. So these are the 5 unique prefixes that I get. As long as the accent for all of them are common, I can use these 5 rules instead of the 10 rules in the table. This is called as the TCAM range expansion handling. So how the table look like? So I started with 1 rule, and destination port number was in this range. I expanded it to 10, and now by virtue of merging the prefixes in the previous example as I wrote, so you get these 5 unique prefixes, and I am taking the action 5. That's how you actually reduce the number of the entries to be stored in the TCAM memory, and by virtue of that you are able to accommodate more number of the rules in the classifier, and you can still use the TCAM memory to do the search operation, which rule to apply. That is exactly the same as that the lookup operation, which we have already seen in the previous lecture. So that is how you handle the different rules and do the classification. So let me do a quick summary of what we studied. Classifier is a collection of rules. Classifier is denoted as with the capital letter C, and every rule has got a predicate and an action, and then the predicates are coming from the attributes of the particular packet, be it the source and destination, IP address, protocol field, port numbers, and so forth. And we said that there are different ways you can build different data structure to do the this classification action. One is the trie-based structures. We saw the hierarchical tries and a couple of optimization, particularly set prune trie and the grid trie. And then we also saw a different kind of the trie structure, which is doing the every classification based on the unique attributes in every field. And then that is, we call it as a field level trie. And then we also looked at the heuristic approaches to do the further optimization. And finally, we looked at the how can we use the TCAM based memory and how to handle the range expansion when we do the when we convert the rules with the port number ranges into the prefix format. So this is all about the packet classification. So in the next lecture, we'll come back and discuss something else in the